let's start today's session. The main problem when we are using the univariate polynomials, actually we used the univariate polynomials until now. We had only x. And the main problem here is that if you have a really big size of data, then it's difficult to interpolate that. And the most efficient interpolation is actually using the fast Fourier transformation, using the roots of unities. But actually it's still pretty slow. For example, actually it's slow like if you have an n data, computing that result actually will end as a n of n. There's a complexity of the fast Fourier transformation. And because of that, recently we started to have another approach using multiple variates rather than using only one univariate. If that, actually we can express the same data in an efficient form. Let's see actually how it works. First of all, we already tried to encode data into polynomial multiple times. So you can think vector is actually equivalent to a polynomial. And then if we try to encode these to a univariate polynomial, it will result like this. Very interpolate those values. Right. This is actually what we have done. And actually we can use a two variates instead of using one variate to express this thing. Let's try to do that. This is something that how we can do. So you have a two variate, x1, x2, and y value. x1, x2, y value, x1, x2. Then we have a four coordinates 0, 0, 0, 1, 1, 0, 1, 1. So in this case, in these 4 0, 0, 0, 0, 1, these four coordinates, actually we are mapping those points in this direction. Then actually we're gonna have a hypersurface. I mean, in this case, we are having a surface, and if we have one more coordinate, we need to think about it in a more in an abstract way. We're gonna have a virtual space, and then in that hyperspace, we're gonna have a hypersurface, just like, which actually will look like that. Actually, we cannot visualize how exactly that looks like, but we can think like, okay, if we have a x1, x2, three coordinates, and if we use x1, x2 for their position vector, and if we just evaluate that at x3, it will look like that surface. Yeah, we are not getting on the same page, right? How we encode vector into a univariate polynomial, just like this. But actually, we can also encode them in the form of a hypersurface.
Hypersurface like a plane.
Yeah, like a plane. But actually, yeah, it's not. Yeah, it looks like a plane. Yeah. I mean, the reason why I'm saying hypersurface is that.
Other degree.
Yeah. Actually, we can increase the degree. The degree of x1, x2, here is actually 1. So actually it can be called as a hyperplane. But we can have a multivariate polynomial where the degree of this x1 is 2, for example. And actually it becomes a hypersurface.
So you have curves.
Yeah, we're gonna have a kind of curve.
Saddle.
You might have
Right, saddle. Yeah, Katie is the expert of this field.
Yeah, it's not SEM. It's a perfect machine.
So here is a transformation between vector and polynomial. We are actually saying the same thing. The first one is we include data in the vector format, and we are encoding the data into univariate polynomial format, and also we can include the data into the multivariate polynomial form.
How do you go from univariate to multivariate?
How actually we cannot directly transform univariate polynomial to multivariate polynomial. We are just thinking like, okay, we can create univariate polynomial from the vector, and also we can create multivariate polynomial from the vector.
Oh, okay.
So there exists an interpolation method from the vector to the univariate polynomial, and also we have an interpolation method for univariate polynomial too. So we can let a multivariate polynomial interpolate the data on the given coordinates 0, 0, 6, 0, 1, 2, 0, 1, 7, 0, 1, 1, 9. Sorry.
Yeah.
So actually this is this picture shows the multivariate interpolation. So we can say these three formats are actually saying the same data. Okay, let's see a little bit more detail. Let's take a look at it in detail. In vector, we have the index 0, 1, 2, 3 here. It's because if we think it as an array, then for the index 0, the value is 6. For the index 1, the value is 2. Like this. And in univariate polynomial, actually we are using x instead of the index here. So we evaluate that polynomial at x equals 1, then it will output 6 and like those. And in multivariate polynomial, we are using a vector. I mean geometrical vector instead of the index or just an x value. So we are giving it a coordinate. And actually that coordinate will be called kind of as a position vector. So for each position vector, we're gonna have its evaluation value. In this case, we have 4 position vectors here. 0.0, 0.1, 1.0, 1.1. In each position vector, the corresponding evaluation value is 6279. And using those things, we can interpolate that into a bivariate polynomial over there. Okay, let's try to understand this in a more visually. Okay. Actually, this is actually visualizing when a multivariate polynomial has only a one-dimensional hyperspace. So we are expressing it in a univariate form. In this case, the position vector actually has only one coordinate. So the value in the position vector is 1, 2, 3, 4, and scalar value looks like that. And if we interpolate that, we're gonna get a univariate polynomial. Let's try to increase the dimension for the domain, one more, then it will look like this. We increase the dimension of it. So the position vector will look like 1.1, minus 1.1, minus 1 minus 1, 1 minus 1, and for each position vector, actually we can assign value like 6, 2, 7, 9, and if we interpolate them, we're gonna get this binary polynomial result. And let's try to increase our dimension one more. Yeah. In this case, we are using 0 and 1 for the position vector. In this case, we're gonna have 8 position vectors. We can also increase, like, we can also use not only 0 and 1, we can also use 2, but in this case, I'm just using 0 and 1 for the position vector value. Then we may have assigned scalar values inside of the, for each position vector. Is there some of us have heard of the multivariate subject stuffs? No? Maybe anyone heard of the Boolean hypercube? Actually, this is called the Boolean hypercube. This is called the Boolean hypercube. So it looks like a cube, right? And it exists in the hyperspace. So it's an hypercube, and we're gonna assign the value into the position vector only 0 and 1. So this form is actually called the Boolean hypercube. Why we're defining this Boolean hypercube? Let me show you a little bit more. Actually, this is a pretty important theorem that we have right now. It means actually, if we let some, if you make some interpolation that interpolates a given data, then actually there exists only one unique multilinear polynomial that interpolates the given data. Just like univariate polynomial. In the univariate polynomial, if you have a 7 data points, then we can make sure that you have only one unique univariate polynomial with degree 6. But you may have another univariate polynomials that interpolates the data which degree is more than 7. Right? So if you have a degree 7 polynomial, you may have an infinite number or the size of field, number of polynomials that interpolates the same data. But actually, if we constrain the degree of your univariate polynomial to 6, then actually you may have only one unique univariate polynomial. If you think about this in the univariate polynomial case, it's exactly same in multivariate polynomial too. If you have a Boolean hypercube, and if you assign values, then actually there exists only one unique multilinear polynomial, which means that the degree of each variate is at most 1. Then you're gonna have one unique multilinear polynomial. That is set as a multilinear. Let's say just a moment. Okay. Here we need to visit what the multilinear extension is to. As in univariate polynomial, let's say you have a 13-degree polynomial. in univariate polynomial, we evaluate them on a given multiplicate subgroup with size of 6. Then or with size of 7, let's say 7. Then we're gonna evaluate them and get the 7 evaluation values, right? And we're gonna have a unique one univariate polynomial with degree 6, which interpolates those same values. Which is the same thing in the multivariate setup. There may exist some multivariate polynomial, which degree of x3 is maybe bigger than 3 or 4. Right? Anyway, if we evaluate all of those values on the Boolean hypercube, just like we have evaluate them at a multiplicity subgroup, and then if we find a polynomial that interpolates those values on the Boolean hypercube, there exists only one unique multilinear polynomial, and that is called the multilinear extension of the original polynomial. I will show you when we use that later.
Does it mean that in each dimension there's one unique or all or n dimensions that can contain one unique
Linear that interpolates a given data set over the Boolean hypercube.
So what does it mean by most efficient? So for example, if I have 4 points, right, then by this definition, the most efficient structure would be to define it over a square in
Yep.
2 dimension, right? But then in 1 dimension, we'll be defining it over a cubic.
Yep.
So what's the efficiency that we're gaining?
The efficiency that we are gaining is that the cost of the interpolation drops down to O of n rather than O of
So
log
the
n.
cost of it.
Yeah. Because the main reason is because we can isolate each dimension against each other. But in univariate setup, actually, we need to multiply terms, and actually it costs the log n stuff there. In multivariate setup, we can actually isolate each dimension, and then actually we can make it much faster than univariate setup.
So, given, let's say, if I have like a degree 7 polynomial and I interpolate it in a multilinear, like in multiple dimensions, right? Like so the most efficient one will be the 7th dimension?
No, the third.
Third, 3.
Because there's 8
Yeah.
points on this.
Okay.
2 to the 3 gives you 8 points.
Okay, got it.
And your 7th degree polynomial
Mhm.
can be expressed in an 8 evaluation points.
I see.
So it's O n, right? Is it cost of
Yeah, the cost of interpolation in multivariate is O of n. While the cost of interpolation in univariate polynomial is O
N log.
n log n.
But does this affect how we can? So in univariate polynomials, we usually use FFT to
Right. To
like improve
interpolate
speed, right?
data.
Yeah, but in this instance of like using multiple
Yeah.
dimensions, does it change that, or we can still use FFT?
Actually, we are not using it here.
Okay, got it.
Yeah.
Yeah.
And I think you may have heard of that. The main cost of Plum or something is kind of creating the commitment. So we always ask like, oh, do we need to commit to the polynomial? It means like it's kind of we need to do interpolate that. Then we need to do fast Fourier transformation. Oh, log n of n of n. It's big, yeah. So that is the main kind of challenges when we are doing the univariate stuffs. But in multivariate polynomial, multilinear extension, actually we can do it much faster way. Okay. So actually, I gave you the definition definition of the Boolean hypercube already. So we usually denote the Boolean hypercube just like this. B sub 1 means that it's a one-dimensional Boolean hypercube, and B sub 2 is a two-dimensional Boolean hypercube. B sub 3 is a three-dimensional Boolean hypercube. So we are evaluating our multivariate polynomial on those position vectors. Okay, using these things, we can do the same polynomial IOP is what we have done using univariate polynomial. So let's see. Say first of all, we can also test the identities between two polynomials via public key protocol. Let's see how we can do that. It's a pretty similar. We actually pick a random number from the field, not from the Boolean hypercube. Yeah, and it refreshes us. So we are picking a some random number. Exactly same. We are picking a random position vector in the hyperspace, and then evaluating them. I'm sorry. Actually, it's a typo. It should be kind of a both are. So the evaluation of the two polynomials actually are equal to each other. It means that we can use the same thing, just like the subversible lemma. And the possibility, actually, if you just isolate each coordinate, then you can easily think about how the subversible lemma will work there. So the D is the at most degree of any coordinate, any variant there. For example, we have a polynomial f, which is a x1 square plus x2 plus y. Then, if you think about x2 as a constant, then it's just a univariate polynomial about x1, and we can just use the same subversible lemma. And actually, x1 doesn't affect x2. x2 also doesn't affect x1. So because of that, we can think of the possibilities actually isolated with each other. It's all of them are actually independent of each other. So the subversible lemma will give us the same equation, just like univariate polynomial. In this case, here is a 2.
So do that for like x1, x2, x3, x4.
Yeah.
We combine them together, like just do one discrete evaluation, like what we learned yesterday. Can we do that? Like, evaluate.
Definitely.
Okay.
Yeah, we definitely can do that too. Batch, you mean the batch evaluation?
Yeah.
Yeah, we definitely do that too. Actually, we have that in the following slide. And definitely we can examine a much more complex relations of polynomials too. Just like this, we just pick some random vector from the field and test that. What does that mean? It means may have a hypersurface. Not the hyperplane. Hyperplane is for the multilinear polynomial. Or actually, just for a multivariate polynomial which has some degree other than 2. Actually, we may have some hypersurface. Actually, they're gonna interpolate those polynomial on 2 degree of a Boolean hypercube. Say 2-dimensional Boolean hypercube in this case. Right, 2-dimensional Boolean hypercube, and its evaluations will look like this, and we have a hypersurface, which is a multivariate polynomial, and we have a 2 hypersurfaces in this case. Like, oh, maybe it will look like this. And actually, if they are exactly a same hypersurface, then okay, let's try to examine this surface at a random point, like here. This is R1, R2. So we pick a random point and then examine that. Okay, what is the value? What is the value? So if they evaluate to same point, then actually it means, oh, it's a same hypersurface. It's the same multivariate polynomial, just like what we have done for univariate polynomial, using the supersimple lemma.
Sorry, the circle x, actual z-axis, you say that it's the evaluation of the Boolean, the 2D Boolean on Z. Yeah, dotted line, the circle x. Yeah,
Last one?
what are those?
Yeah, okay. We have a 4 data point.
Yeah.
4 data, 6, 2, 5, 7, for example. To express this a multivariate form, we're gonna map this data into a 2-dimensional Boolean hypercube. 0, 0.0, 0.1, 1.0, and 1.1. So to express them, they becomes like 6, 2, 5, 7. Yeah. So we have a but actually this is when we are interpolating this into a multivariate polynomial. But in this case, we are assuming that we have a multivariate polynomial. We have some multivariate polynomial, and then actually that multivariate polynomial is evaluating at this Boolean hypercube, and their evaluation values are like this.
So that hyperplane also interpolates this small point.
Yeah, we are actually thinking about 2 different multivariate polynomials. We are thinking about 2 different hypersurfaces, and it's a hypersurface actually that interpolates the same data set, but actually there will exist only one unique hyperplane that interpolates. Yeah.
So any surface, like
Yeah.
one other plane.
For example, if you have a 2 points, there exists only
One line.
yeah. If you yeah.
But there can be multiple.
Right. You have only one. Oh. What does the
This is supposed to be 2-dimensional.
I mean, if you have a 2 point, you have only one line. But actually, we can express a lot of way like this. Yeah. But there is only one line. So in this case, there exists only one plane that interpolates this thing. One plane, but actually there exists many surfaces that interpolate those points. So actually, we are thinking about, for right now, we are thinking about 2 different surfaces. We may have 2 surfaces, and checking that 2 surfaces are actually a same surface is that, oh, let's try to pick a random or just like univariate polynomial and checking. Just like that, we are picking a random position vector and evaluate those two different hypersurfaces. Actually, for right now, we are not interpolating. Let's do not interpolate. Let's just say that we have two different hypersurfaces, and then checking that two different hypersurfaces are actually same surface is that checking them, evaluating them at a random position vector R, just like what we have done in the univariate polynomial, and then the evaluation equals to each other. Oh, with that possibility, they are actually a same hypersurface.
Just asking, do you need to check multiple R's? So for example, because the chances for it to be like having two different surfaces have the same R is very low right now. Do you still need to check multiple R's?
So, actually, I think that if we choose R1 equals to R2, there may exist some vulnerability. I think.
How do you know how many R's do you want to choose for this check? So you
How
are
many
trying-
R's?
Yeah. How many
Only
R's?
one point, but actually
One
two.
point.
Yeah, but 1 point needs to pick a two field element because we are having this
Oh, because it's a-
because of bivariate polynomial.
I see.
The degree there means the degree of what?
Degree, the at most degree of each variant.
At most.
Yeah. For example, yeah. If this hypersurface looks like
It's degree 3.
then actually the D is 3, and in case yeah,
It's 2.
the D is 2.
Can we do THMA or?
Yeah, Shamira, for picking random.
Yeah.
Yeah, definitely.
We can also just pick one random bits and do like square, like for all the dimensions. I mean like, and then manipulate it for all the
Yeah, maybe we can pick one random and create a different randoms from there. But actually, if it has some algebraic structure inside of it, then it may increase some algebraic, some vulnerability. Because it may be able to get defected or something, and those things actually increases the vulnerability. So because of that, when we try to pick some random, then we try to use the hash function as much as possible to break the algebraic structure inside of them, because they are all about the addition and the multiplication. So if they have any algebraic simple simple structure, then it actually has some vulnerability inside of it. Yeah. And actually, we are not using pairing when we are doing this the polynomial IOP check. And I'm gonna show how can we check this without using pairing. Great. Okay. And let's think about how to bind the range. In univariate polynomial, actually we have used the multiplicate subgroup to bind the range. It means like, oh, your L or O, you have L or O, and actually L times R is not actually O, because L is a kind of a 3-degree polynomial, R is a 3-degree polynomial, and O is also a 3-degree polynomial. So because of that, definitely L times R minus is definitely not equal to O. But actually they will be evaluated to a same values for the given range. That is how we bind the range using Z of X. Right? Shall we visit that again? Maybe I think it may give us a complete sense. L is a kind of an AX cube X square. R say and O is something like yeah. And anyway, it's actually interpolating the values like 3, 2, 4, 1. 1, 2, 3, 4. It's actually 3, 4, 12, 4. We just wanted to express this relation using QAP. So, because we just wanted to make sure that, oh, actually this actually satisfies the Hadamard product. 3 times 1 is 3, 2 times 2 is equals 4, 4 times 3 is 12, 1 times 4 is 4, and we are interpolating this to L, we are interpolating this to R, and we are interpolating this to O, and checking that actually holds true was the QAP one, right? But actually, if we multiply these two polynomials, this is actually not O. As we can see, the degree is different. This is a degree of 6 and this is a degree of 3, so it's definitely different. But actually, they will be evaluated to a same value. They will evaluate the same value for the multiplicative subgroup. For the multiplicative subgroup. So we are binding the range to this multiplicative subgroup. So how to bind L times R minus O actually will be evaluated to 0 only for those ranges. Because of that, Z that vanishes to 0 in this multiplicative subgroup and times a quotient polynomial is actually how we bind the range to this multiplicative subgroup. So L times R will not actually evaluate to the same value to O out of this range, but they're gonna evaluate to the same value in this range. This is actually how we did how we bind the range in univariate polynomial. And in multivariate polynomial thing, actually we bind the range using the Boolean hypercube. So actually we have some limitation. So we cannot bind the range with like only 13 elements. We can only bind the range using 16 elements with the powers of 2. So actually we are actually wasting a 3 sides there. So for example, like if you have a 2 to the 32 like very big value, which is about like 16 billion, right? Then actually in this case, maybe you may be actually wasting kind of around 7 billion points. It's yeah, because we have a limitation how to bind the range.
So you, instead of going to 32 because it's in the multiples of 2, you try to go lower to reduce the amount of space you are wasting. Right? So you're trying to reduce the size of the additional space you are wasting by trying to constrain it so that it's a lower value for this powers of 2. Yeah.
Actually, I didn't get your exact question.
So because we are using a hyperbolic cube to do this, and as you said, we are wasting a lot of values, right?
Yeah, there's some potential
Yeah.
to raise.
So when you use this, then you will try to not go to the next values when if it exceeds by a little bit, we'll try to reduce it instead.
Yeah, actually, yeah, maybe we need to do that sometimes. But even if we are wasting a little bit, maybe we are kind of using a maximum kind of twice, but actually it's less than the log n. What is the log n of this? It's 32. Okay, it's twice is much better than 32 times. Yeah. Actually, it's maybe the size of the data might be a little bit overwhelming sometimes. Okay. And now I'm gonna introduce what the sum check protocol is here. Actually, we already did a pretty similar thing in univariate polynomial. Actually, we have done the grand product check. Hello, Chi. Yeah. Actually, we have done the grand product check for the plum, and actually because it is used for the grand permutation check. And before we go to the grand product check and grand permutation check, also actually we did the grand sum check too in univariate polynomial, but actually we haven't used that. But in multivariate setup, actually we are using the grand sum check. Let's see. I mean, before we go to the sum check protocol, let's think about why we are using grand sum check here. We are actually checking the grand sum is 0 almost for most of the day. Which means, for example, let's say we have two different polynomial, two different multivariate polynomial, two different surfaces, but actually, interestingly, they evaluate to same value for all of the Boolean hypercube. Just like, let's erase that. We have two different hypersurfaces, but actually, interestingly, they are evaluated to a same value for a given Boolean hypercube. Let's draw that again. Let's draw that. So we're gonna use a two-dimensional Boolean hypercube. So we're gonna have a 0, 0, 0, 1 like this, and then we have a two different hypersurface that looks like this. One looks like that, and the other actually looks like that. Yeah, two different hypersurfaces. But interestingly, the evaluation at the Boolean hypercube, actually they evaluate to a same value. Yeah, this is something related to LR, evaluate to the same value with O. Yeah. So LR is this one. L times R is the red one, and O is the blue one. Yeah. So LR actually evaluates, let's say LRO. 1, 2, 3, 4. 2, 2, 2, 4, 6, 8. actually this is the situation that we want to try to check. So yeah, we have two different hypersurfaces, and they are actually interpolating each given point LR O, and this red surface is kind of a L times R, and blue surface is just O. And actually, they will get evaluated the same value for this Boolean hypercube. This is actually what we are trying to do, and we cannot use the same technique what we have done in univariate polynomial here. The technique that we are doing here is that we cannot use the same technique. So what about this? What about L times R minus O? Let's try to evaluate that at each Boolean hypercube. Actually, they're gonna evaluate to 0, right? For the Boolean hypercube. Then, okay, for each Boolean hypercube, but there also exists some potential, like, before that, let's try to summate all the evaluation. It will return 0, right? Okay, this is actually called the grand sum of the evaluations of the multivariate polynomial. But actually, even actually it outputs the grand sum to 0, actually it doesn't make sure that all of these evaluations are actually 0, because some of evaluations look like that, and actually the grand sum becomes 0, right? How can we prevent this? How can we prevent this? Yeah. So what about multiply some random? Multiply, okay, then rather than summate this thing right away, let's try to multiply this with some random polynomial. Random polynomial. And actually it should output 0 anyway. It should output 0 anyway. Because they will return always 0. Or any polynomial. Or any polynomial.
But I mean, like, is it just one polynomial that is?
Yeah, we can think about this as a one polynomial. And actually, it will return, it will evaluate it to some random point for the Boolean hypercubes. But actually, the first term will always give you 0. So the grand sum will actually always 0.
But what if the first half doesn't give 0? So if the first half doesn't give 0,
Right.
give 3,
Right.
it's
Yeah. Actually, if this the first term is not giving you 0, then the grand sum will not be 0. So this is the polynomial that we want to check. It evaluates to 0 for the given Boolean hypercube. We can check that by, okay, let's try to multiply that with a kind of a random polynomial, and then let's try to check the grand sum again. And then if the grand sum actually give us 0, then it may be actually all of these evaluations in the Boolean hypercube is actually 0. Yep. But actually we have a pretty effective technique to choose this polynomial thing, and I'm gonna actually share that too. So some track is that we are evaluating a given multivariate polynomial for all of the elements of the Boolean hypercube. So in this case, you can think the summation is 6 plus 3 plus 2 plus 4, and actually becomes 37 in this case. And what we are going to do is that the total sum is actually 37. This is actually what we're going to do. Then how can we check effectively? This is the protocol. This is called the sum check protocol to check that in a very efficient way. So actually we're gonna actually use a divide and conquer approach here, but for each variate. So for the first time, we're gonna think about only the x1 as a variate here, and then let's try to summate all the values like from x2 and xn. Actually, we are evaluating them there. We are just thinking that x1 is only the variant here. And if you compute them and summate them, you're gonna have a one univariate polynomial. If you compute the univariate polynomial, then you can evaluate them at 0 and 1, and if you add those two values, then actually it should be equal to the grand sum. Does it make sense?
Sorry. Why is 0 and 1 equal? Is it because of the hybrid? Why is 0 and 1?
Why is we are actually doing the Boolean sum check on the Boolean hypercube. Yep. So actually we didn't do the summation when x1 is 0 or n1.
That notation, the degree 1 of f means the highest degree of the first dimension in f, right? The degree 1.
Yeah.
Okay.
Right. Or we can think this equation like this. Sum of when x1 equals 0 to x2 xn and x2 xn is in a Boolean n minus 1 hypercube plus sigma f1 comma x2 xn and x2 xn actually an element of a n minus a Boolean hypercube. Actually, it should equal to the sum. It should equal to the total sum. No? Let me write here. Let me write equation. The total sum is definitely the sigma of x1, x2, xn is in the Boolean hypercube, n-dimensional Boolean hypercube. Right? This is the grand sum. We are evaluating them, the f all over the Boolean hypercube. And we can divide this into a smaller thing like s equals when x1 is 0 plus when x1 is 1. We can divide that into 2.
hypercube, can I assume that the Boolean hypercube essentially decides that if the value exists in that, or if that variable is existing in that specific space? So we are doing 0 and 1 because it's in the Boolean hypercube, which somehow acts as a selector that selects, hey, this value exists or not. Is it? Or am I understanding it wrongly?
I
am understanding it wrongly.
What's
Yeah.
the equivalent of Boolean hypercube in this case?
in this case.
Versus in univariate, let's say.
Okay, let's say. In this case, grand sum is 6, 2, 5, 7. What is the grand sum here? 8 plus 20. Grand sum is 20. Right? Then let's say this is the x1 and this is the x2. And I'm gonna, let's try to divide them. Then x1 is a variable, only the variable that we're gonna think about here. Then when x1 is 0, this is actually when x1 is 1. So actually we're gonna sum this part first, and we're gonna sum this part later. This is when x1 equals 0. This is when x1 equals 1. So we can write this as okay, the value here will same that f0 and x2 equals 1 or 0, and this can be written like this. Right? So it's a summation of this one and this one. This is actually the value is 8. This value is 12. So if we add these two values, then it will give us 20. Right? X1 is a variable. Is a in this hyperspace.
So why is it that when you put 0 you can say that represents the left, and when you put it as 1 you can represent it as the right side?
That's
That's
the
the
first order.
Okay, so that explains it.
Yeah. So if we divide this point into actually two parts, then actually we can think one variant as a variable. X1, in this case, X1 as a variable. So we can rewrite that just like this. X1, okay. We can actually think X1 is this part becomes a F1 of X1. So this is, sorry, just a moment. This is actually F1, 0. This is 1.
So how do you check the last part? The sending R1, because I don't know what F is, right? So even if I send an R1, so I still can't know whether it has been changed. Like how do I make sure that the F1 is from F?
That's F1 is actually from F.
Without knowing it.
Actually, we should go that to the final round. This is the first round, and if we go to the final round, then actually we can make sure that this is actually from the F.
Why one question. When we do this calculation of using 0 and 1 for f1, we are not directly operating on the multivariate polynomial that we have for this, right? We are basically taking the multivariate polynomial, separate into multiple univariate ones, and
Right.
then computing them. So this step actually produces a value from this univariate variable instead of like perhaps another polynomial, because it's complete, right? So in this case, the grand sum here from this single polynomial, it doesn't produce the grand sum of the entire multivariate polynomial one. It only computes for that dimension, right? So
Yeah.
in this case, let's say 0, it's 6 and 2 is lying on the 0 part of this. So in this case, f10 plus f11 will be equivalent to 6 plus 2 instead of equivalent to 20. Is that the case? Because we are operating on one dimension of this, right?
Yeah. I mean, in this case, so f1 of 0 should be 8, and f1 of 1 should be 12.
Okay.
So 8, so because 8 plus 12 becomes 20.
Oh, that's for the.
Let's think about it this way.
Okay.
When you have a 4 point,
Okay.
and would you please interpolate them into a multivariate polynomial thing? Maybe it's okay that it's not a multilinear. It's okay. You have a multivariate polynomial, then interpolate actually the data point on the Boolean hypercube. And then, please give me your grand sum. What is your grand sum? Say
20.
20.
Yeah.
Okay, thank you. Actually, I would love to check that you are saying the truth. So at the final round, you're gonna give me a point at a random evaluation at a random point. I mean the evaluation of your polynomial at a random point at the end, at the final round. And to compute that, actually I'm gonna ask you something first. So you have your grand sum 20. Would you please make a univariate polynomial regarding to the first variable x1? And how to make it? Okay, x1 is a variable, and x2, x3, etc. actually will not consider as a variable.
It will become constant.
We're gonna make them kind of as a constant. How to make them constant? Okay, evaluate them on the sub-Boolean hypercube.
Okay.
Everything, and give me the grand sum of your all the evaluations.
Got it.
Then you can give me the univariate polynomial only actually depending on x1.
Got it. Yep. Thank you.
And then if you give me that polynomial, okay, thank you. I'm gonna evaluate that at 0 and 1. And if you gave me the correct polynomial, the sum of f1 of 0 plus f1 of 1 should equal to the grand sum actually that
20.
you gave to me. This is the first round.
Okay.
So if the evaluation of when comes first univariate polynomial f1 actually doesn't give me the grand sum like that, then actually when comes cheating. Yeah.
Then do you continue with x2 and x3?
Right. Exactly. And then how to continue that? This is the second round. So to continue that, okay, thank you. I have a univariate polynomial f1 of x1. So in this case, okay, I will examine you with a random number now. I pick a random number, R1, and I'm going to evaluate your polynomial, univariate polynomial f1 at R1. Actually, you can do that same, because you have the multivariate polynomial by yourself. Okay, so I'm gonna evaluate that at R1, but actually we can make x1 is also a constant. Because putting some value, fixing a value for x1.
Basically, you fix value for every other thing when you compute specifically for one variable.
Yeah.
Yeah, got it.
Let's see. Okay. Okay. This is the second step. Because I pick the first random value for the x1, I'm gonna put the random together. We're gonna put the random together. Wenkan will put R1 to the x1 always, and I'm gonna put R1 to the x1 always. And then we're gonna think x2 is a variable for right now. We're gonna do the same thing. Wenkan, yep.
What if the R values are the same?
Verifier, if what the R values are same for the all the round, as it introduces some algebraic vulnerability. Because R1, R2 has some algebraic relation between each other, it becomes a vulnerability.
So they have to be extremely random.
Yeah, in a very random. Yeah, so you usually use hash function for that. No, it's a, yeah, randomly from the field. Yeah. R1 is randomly from the field. Then, okay, Wanka, would you please put R1 to your x1, and then would you please try to compute your second univariate polynomial f2 of x2 by doing a grand sum regarding to the x3 to the xn for those sub-Boolean hypercube.
Yeah.
So Wenkan, yeah, thank you so much. I got your f2, and if you give me your f2 correctly, I'm gonna actually test your f2 by evaluating that at
F1.
0 and 1. And if I actually add them both, it should actually return the f1 value. f1 of x. Yeah. So, yeah.
Yeah. In this case, it's R because we are choosing a random value for this case. We are fixing a random value for F1, X1.
Yep.
Yep, got it.
So for the first round, actually we check the consistency using the grand sum. In this case, we are checking the consistency with the evaluation of Wenkan's first univariate polynomial f1 at the random r1. So if Wenkan gave me the correct f2 univariate polynomial, then if I examine that by evaluating at 0 and 1 and sum, actually the value equals to f1 of r1. You're actually, Wenkan, you're keeping the consistent thing. We can keep this thing until the final round. And definitely this is for the third round. We are for the third round, we put I put another random and do that again, do that again, do that again, and then the final round actually look like this. We can actually give the final univariate polynomial f n minus 1 of x n minus 1, and then f of n and xn. Then I'm gonna evaluate that at r n. And after that, I will ask to Wenkan that, hey Wenkan, would you please give me your opening proof of your multivariate polynomial at R1, R2, R3, at Rn?
Yeah.
Let's check actually same. So we need additional polynomial Kalman scheme for multivariate polynomial here, and we need a opening scheme for the multivariate polynomial scheme, Kalman scheme. We are assuming that we have that already. We are assuming that we have already a multivariate polynomial Kalman scheme, and it's appropriate opening proof method for multivariate polynomial. So I'm asking, oh, when can actually you already computed your polynomial, thank you. And then using the oracle, I'm asking you evaluate that at a random vector R1, R2, Rn. Oh, thank you so much. You gave me the value with the correct proof. And then, oh, actually, this is actually exactly same what we have examined during the subject protocol. These steps.
Can you explain R1 with this example?
R1.
Yeah, like how that changes so that F2 0 plus F2 1 is equal to F1 R1.
In this case, maybe we are checking R1 here. And Renka actually will give a univariate polynomial for univariate polynomial, and actually it will look like this. I mean, we are just looking at we are just taking a look at here, and then actually when we pick the R2, it's something that we are looking at this space in this way. I mean, at first, if you actually take a look at the this space in this direction, actually it will look like this. And we are actually making that into a one line by summing everything to one line. I mean, in this case, let's say we have let's say in this way, we got a first line here, and we have actually second line here, when x1 equals 0, and this is when x1 equals 1, right? Actually, if we see the space from this point, then this is when x2. When x2 equals 0, we can see this line, and when x2 equals 1, we will see this line here. And we are asking when come that, oh, just give me one line. Right, just give me one line. Actually, we are actually using that as a multilinear setup, so maybe it might be kind of some curves or something. But anyway, when come, I actually seeing a duplicated curves or lines here. Just give me one line. And Renka actually giving me this line. This is the f1 of x1. And then f1 of 0 actually should, I mean the line is the summation of these two lines.
Should give you F1 R1.
Yeah, it actually f1 0 gives us 8, f1 1 gives to 12, and actually I'm examining that at R1, and actually it will give some random number. f1 of R1.
Right.
Yeah.
In the first round, when you are calculating for x1, everything else is fixed at I guess a certain default value that we know will result in the grand sum of 20, I guess. And then in the second and subsequent round, instead of using the first grand sum of 20 from the first round of 0 and 1, you start calculating, let's say, just choose a random number so that you get to connect them without directly using the same number.
Right. But actually, I think this is a really good explanation. Let's try to draw again without from scratch. Okay. This is x1, x2. And let's say, actually this is polynomial plus 1, 0, 1. Okay. And let's say there is some evaluations. Like this. evaluations. Okay. And if we try to see only the x1 is the variable, then actually we are seeing like this. We are seeing like this. In this case, we can discover two lines here. Like this. We are discovering two lines. Yeah. So it'll look like that. Yeah. Let's say this is 6, 5, 4, 3, for example. What we wanna do, actually, what we wanna do is actually summing everything, right? So we are asking Wanka, oh, I would like to check only x1 first, but actually I am seeing these two lines. Would you please sum these two, add to this line into one line? And actually Wanka is giving me, okay, there is a, if you see like this, your 6, 4, 5, 3. Actually, you are seeing like these two lines. This is x1 and this is y. You are seeing these two lines, and this is when x2 equals 0. This is actually x2 equals 1. You are seeing these two lines. Okay, rather than having these two lines, would you please make one line by add these two lines? Actually, we are having like this line. Okay. This is actually the sum of these two lines. Right?
F1, 0. That's the 1, 1.
0. Yeah. It's a, actually the value here is should be 11 and 4, 3. The value here should be I'm sorry. It's it's kind of abstract art. So we are having a new line. This is the f1 of x1. In this case, okay, thank you, Anka. Let's try to examine that. I'm gonna put 0. So you're gonna be 11. I'm gonna put 1. You're gonna give us 7. And the sum will be 18. Actually, it is actually equal to this sum. Okay, thank you so much. And then, let me pick one random here. If I pick a random here, actually it will give me the f1 r1. Right? Okay. Then, let's try to take a look at the x2 as a variable this time. And okay, x2 as a variable. Okay, actually we have these two lines. So if we say y and x2, it will look like, okay, when x1 goes 0, 5, 6, and 3, 4. 3, 4, 5, 6, 5, 6, 3, 4. We have these two lines. If we just see x2, but we also don't want these two lines. Rather than actually having these two lines, let's see this at r1. This is when x1 equals 0. This is when x1 equals 1. And what is actually x1 equals r1? Let's just say that, oh, actually this looks like this. This is when x1 equals r1. Yeah. And this line becomes the f2, x2. We are seeing, actually we are fixing x1 to r1. But thank you, Chris. I think this explains what's actually intuitive and the others.
Calculating essentially each slice of the plane,
Yeah.
and then you're introducing random numbers so that there's no vulnerability. Because if you don't introduce that, it will just always be plenty, and you can, I guess, game it a little bit. Yeah.
we now actually want to check only the F2 to make x2 as the only variable here.
We're going to consider x1 as previously.
X1 is now constant.
Yeah.
Yep.
We're going to check x1, so we're going to fix that, and then now check x1.
Yeah. We already checked the x1.
Yeah.
I mean f1 of x1 actually gives us the information about the grand sum already.
Yeah.
So we already checked the grand sum.
Yeah.
If Wenkan gave me the f1 correctly, and I am checking Wenkan actually giving me f1 correctly. So to check the f1 is correct, actually,
Right.
I'm just doing repeatedly until Wenkan can give me the final evaluation.
Okay. So F2, X2 is to actually check F1.
Yeah,
Okay.
F2 is actually to check f1.
Until the end, Fn how we check the last step.
Yeah, and for the we may have the last fn of xn. Actually, using that, we are checking fn minus 1 is correct. And how to check fn? Fn of Rn actually will equal to f of R1, R2, Rn. Using this, Wenkan, I need additional proof of your opening of your multivariate polynomial. Please evaluate polynomial at R1, R2, Rn and give me that your proof. Give me your proof for your opening. Then we can make sure that each of these intermediate univariate polynomial consistently actually correct while checking the grand sum for the first round.
You can use the numbing approach of using like the polynomial coding scheme and some of the coding scheme to check F1, F2, F3, F4, but it's just not efficient. So you just check Fn.
Right, true.
Okay.
So we only do one commitment. We only use the commitment scheme for the last step to
Right.
FR
Correct.
to FRN.
Correct.
But previously it's all sum check.
Right. Okay, I think that before we go to the detail other polynomial IOPs, I think it is crucial to understand the subject protocol step by step. So let's have a lunchtime plus breakout sessions to understand actually how the subject protocol works. Yeah. Yep.
Thank you.
I naive example of how to do the Fiat summary transformations for just picking the next random first. Yeah, and this is about the multilinear extension actually that I explained in the morning, that just like univariate polynomial, there is only one polynomial that interpolates those values on the given Boolean hypercube. That's a multilinear extension, and actually it means that we can derive a multilinear extension obeying some hypersurface. So any hypersurface will have one unique hyperplane that interpolates the same point over the Boolean hypercube, right? So this is called multilinear extension, and yeah, this is the exact some definition of the multilinear extension. So you have a multivariate polynomial small f here, and actually you're gonna have a multilinear extension. So it is kind of it will have some degree more than 2 or 3, etc. The hypersurface, but actually this is its corresponding hyperplane, unique hyperplane. Actually that evaluates to the same value for all of the Boolean hypercube. plane, but we may have a infinite number of a hypersurface that in the place the same points there. Exactly same vertices there. And we use the F tilde for the notation. So if you see the F tilde, actually the tilde means that, oh, it's a multilinear polynomial. So the at most degree is 1, always. So if you see, okay, there is some F tilde, oh, it's a something corresponding multilinear polynomial for a given surface. And here is actually how to make the multilinear extension in an easier way. We can define some special polynomial. So actually, if the f has a n variant polynomial, we can try to define a 2n variant polynomial. EQ is a 2n variant polynomial. So the first n variant is, we can also actually name that as x, and then for the later part, let's denote them as y. And this is actually how we design this special polynomial. So EQ is a unique multilinear polynomial. So we have only one EQ polynomial for a given Boolean hypercube. And actually, it interpolates the vertices like this. It gives you 0 when the first part and the later part actually different. When the first part and the later part is equal to each other, it gives you 1. Yeah. This is the equal polynomial. Then what happens? If we just multiply this special equal polynomial to the original polynomial, then actually it will give you always the same value for the Boolean hypercube. But it will not give you some values for the other vertices out of the Boolean hypercube. So because of that, if we think about that, the sum of the f of x multiplied by equal polynomial is a multilinear polynomial regarding to y. And then f tilde of y actually will give you the same value for all over the Boolean hypercube with the original f of x. This is actually how we can make the multilinear extension. F tilde of y is a multilinear polynomial, and when x is different with y, it will return you 0. So anyway, if you sum everything, it will be 0 only except when x equals to y. It's because of that, actually it gives you the same value compared to the f of x. Yeah. This is the multilinear extension. And do you have any sense here? I mean, let's see the example of the QAP. L, let's say L is a multilinear polynomial that interpolates some points. Let's say 635. R is a multilinear polynomial that interpolates like something. Then let's say that, okay, L is a multivariate polynomial of x1, x2, and x3. R is also the multilinear polynomial like this. O is also a multivariate polynomial. Oh, yeah, let's say we just have an 8 values. Sorry. Like this. What do we want to do? We're going to do the Hadamard product, right? So we love to multiply them. And it's not multilinear polynomial anymore, right? But actually, it will be evaluated to the same number with the output polynomial. So we would love to minus this with output polynomial. And then we're gonna bind the range only to the Boolean hypercube. We're gonna bind the range only to the Boolean hypercube using the equal polynomial.
So, but the Boolean hypercube is. So the Boolean hypercube, it's all the 0 and 1 values, right? You're using that to bind this.
I mean, exactly saying it will look like this.
Where y is the Boolean hypercube polynomial?
Y is an additional variables, and you know that we explained about the how to bind the range before. Here, actually, this will be the kind of a random numbers here. I mean, we are actually examining this relation only for the Boolean hypercube, only for the elements on the Boolean hypercube, right? If this holds true, it will become 0. If that is true, right? It doesn't matter actually what is multiplied by behind. So it will always return 0. So if we do a sum check, if we do grand sum check of this thing, then actually the grand sum should equal to 0.
Yes.
Regardless is actually what is multiplied by the second term.
Yes.
So it will hold true always, 0. And actually, we are just choosing the second term as the equal polynomial here. Then let's see actually what happens here. We're gonna put random vector to the y value. Let's say we are actually putting some random vector to the y. And if we examine that, and for example, if we evaluate that at some point on the Boolean hypercube, then actually this will give you some random number. Because of this, the second random term. Because this equal polynomial gives you 0 or 1 for the Boolean hypercube, but actually it will give you a different, some random number for out of the Boolean hypercube on the field hypercube. So actually, it should hold true to 0, even if we just put some random r into the second letter part of the equal polynomial. Actually, if it holds true, it means that L, R will actually evaluate to O for all over the Boolean hypercube.
Can we reuse the randomness that we used to verify?
Not recommended.
So it's two random types, right? Because when we do the sum check,
Actually, we can do that, but not recommended. So we need to actually pick another random, which is different with this random. Okay. After that, we're gonna do the sum check. Then we're gonna pick another random from the interactive protocol. So we're gonna pick R1, R2, R3. Actually, that will be different with this random actually picked by the verifier at the beginning of this protocol. Okay. Does it make sense to everyone?
Can you elaborate a little bit on evaluating on the Boolean hypercube for that specific L times R minus O?
Okay. L R minus O. For example, let's say we are evaluating that. Okay. 0, 0, 0, 0, 0, 1, 0, 1, 0. For those 8 points. L, R, O, 3, 5,
Okay.
15. Actually, this is actually what we want to see.
Okay.
So if we minus this, actually it will give us 0,
Yes.
right? But what if 3, 4, and 5, and 2, 4, and 5, 3, 3, and 9? No,
No.
11. What about this?
And that doesn't hold
Actually, it's a
value.
+1. I'm sorry. +3.
This one is negative out of its yeah.
-3. So if you look like that, if we sum every evaluations, actually it will still hold 0. But this is actually not the, this is kind of, it's holding some false. We love to check that every L values times R values should equal to these output values. This is actually what you want to check. So to prevent that, this actually returns 0. I'm gonna multiply a random value here,
Which is what we've done
like
just now.
3
Yeah.
or 4. Oh, unfortunately, yeah. But, yeah, maybe some different.
It's 2, I guess.
2, 1, -3. Let's see. Oh, does it still think? I mean, I'm sorry.
You have to have different R.
Yeah, different random.
Yeah, different random,
Yeah,
yeah.
not the same random. So like multiplying 8, multiply 1, multiply 2, multiply 3, multiply 4. So it can be kind of some random, right? How to make this random is using kind of an equal polynomial.
So it serves two purposes, right? First is to make sure this, but also to reduce the dimension.
Yeah, exactly. So the reason why we are using equal polynomial is that actually actually it's adding this, multiplying this random number. So actually we can show that, and actually it evaluates to 0 for all over the Boolean hypercube. Along with, if you think about only the second part, it's still a multilinear polynomial. It's a multilinear extension. So we can do something very easily. Only for the Boolean hypercube. But actually we are putting random R, which is out of the Boolean hypercube. So actually it starts to output some random field element there. The equal polynomial will give us 0 or 1 only for this Boolean hypercube. Interesting. So actually, if we just multiply this equal polynomial, actually we can achieve two things. First one, okay, if actually after multiplying this equal polynomial, it's still if it still satisfies the grand sum equals to 0, it means that each evaluation of the element of the Boolean hypercube actually holds true. And also, we can do some sum check protocol easily using this. Just thinking this as a kind of a multilinear extension thing. So this is actually what we have done for Tonk, and for isn't it? We just designed L, R, and O. This is actually what you have done. So it's all. So if we use this technique, then we can transform the existing Planck protocol to a hyper-Planck protocol.
I see.
You may have heard of the hypernova, hyper-Planck,
They use
hyper something. It means like, okay, we are using multivariate polynomial. And we can design these polynomial equations, polynomial relations in so many creative ways. We are just defining the multiplication relation between 3 polynomials. We may have kind of a 5, 6 polynomials, and we can try to define the relation between that.
In this case, using hypercubes.
Yeah. Using this approach.
I see.
The reason of using a multivariate version is that it's more efficient.
Yeah, it's very efficient to interpolate them to this small L. I mean, this multilinear L, multilinear R, multilinear O is very efficient.
When you say designing different versions of polynomials, what are the advantages that you have for different versions? Like, can you give an example?
Yeah.
Possible to be done.
Okay. It's let me share a little bit about the local writing now.
Oh. Sorry, one more question about this. So, is it so for the hypercube? It will always be 0, 0, 0, 0, 0, 1, and
Yeah, 0 or 1.
okay. So can I increase the dimension of the hypercube to do more than 3 degree, like 3 variables?
Sure.
Oh, I see.
But actually, when we try to compare, this L or O actually should exist on the same dimension.
Okay, got it.
Yeah.
We are computing. So one more dumb question. Why is it? Why is the cube having the dimension of 0, 0? Like, why is it a cube, so to say?
Actually, we can also try to use -1 and 1.
Okay.
Or maybe, okay, we can try to use a 2-degree multivariate polynomial. For example, okay, not only just interpolating polynomials to 0, 1, what about 0, 1, and 2? We can make it.
Oh, you
Definitely. Definitely we can do that. But that is not efficient.
Ah, okay.
That is not efficient. Actually, if we do some, if we analyze the complexity of our computation, the optimal case is actually when we are using the Boolean hypercube.
Where it's linear and it's very nice to deal with
Yeah.
because of the
And also, rather than using 1 and minus 1, actually using 0 and 1 is the most efficient for many cases. Yeah, because actually if you put 0, it cancels the terms every terms, right?
But you can always stretch the dimensions such that it becomes, like you can always project it onto zero. So it's the same thing, right? Whatever point, even if you pick a weird shape, you can still stretch and transform it to become zero.
Yeah, we can just I get it. Yeah.
So definitely, actually, we can also use the we can try to interpolate those things on a another hypercube, not the Boolean hypercube, using the multiplicated subgroups hypercube. Or like, for example, using a third root of unity, maybe okay, omega to 0, omega to 1, and omega to 2, and then we can let some surface interpolate using those things. But actually, yeah, the most efficient case is that actually if we make it Boolean case. Yeah, that is the reason why we are using Boolean hypercube instead of the hypercube. And maybe shall we introduce the kind of the other usage of the defining the polynomial relation?
Yep.
Okay. So actually, this is something a very new research that we are doing, and we actually haven't published this yet. So let me just share that.
It's recorded.
Is it getting recorded?
Yeah. Don't worry. I'll make sure to let you take a look before I send it anywhere.
So, yeah, just please keep this not being published yet.
Okay. I can stop recording.
Yeah.
Okay.
Sure. So, I mean, actually, everything is based on this zero check because we are actually checking the identities, and if we just move something from the opposite side, then we are just checking 0 every time. So zero check actually plays a really foundational role when we are dealing with the polynomial IOPs. So this is actually what we have done. And I just introduced the, we're gonna put the random R to the Y, then actually we're gonna get the F hat there. And we are actually doing the sum check for F hat. Actually, if the grand sum of the F hat is 0, it means that f of x will evaluate to 0 all over the Boolean hypercube. It doesn't mean that f of x is a 0 polynomial. It will have a different point for other vertices out of the Boolean hypercube. So it's something like this. So we have a Boolean hypercube here, and we have another point here. So the surface actually look like this, and just interpolating these zeros at the Boolean hypercube, but actually interpolating other values out of the Boolean hypercube.
Actually, within the constraint of the cube, it's always 0. Within the constraint of the cube, it's always 0.
Cube?
The Boolean hypercube.
Yeah.
Yeah.
Yeah. So actually, this is actually what we've done. I mean, the R and R prime is something that R prime is picked by the verifier at first, and R is a random during the subject protocol. So R1, R2, R3 that we are picking during the process. And this is about the multivariate polynomial Feynman schemes, and basically we can use the same approach using KGG. Yep. And this is about the product check. Actually, we should be able to do the product check, to do the permutation check, to do the Planck wiring.
Okay.
Right? So if we can do product check, it means that we can do permutation check. It means that we can wire some values. And the permutation check with the indexed permutation check. So we should be able to define which index is a permutation of which index element with each other. So, okay. Yep. This is actually a very clever invention from the hyperplane. So, can you get actually what does that mean exactly? Right? Maybe.
Well, still reading about
Yeah.
Sorry.
So, we are defining a new auxiliary polynomial, just like what we have done in the Planck. We define the t. In this case, we will define another polynomial v.
Such that
Yeah, just like we define t. And a little bit differently with the univariate polynomial. Actually, in the univariate polynomial, we started from 1, and then we moved to the next root of unity, next root of unity, next root of unity by multiplying root of unity to the x value. In this case, we're gonna say that, oh, we have some values, and then just like Merkle tree, isolating each axis, and just like Merkle tree, we're gonna multiply them, and then we're gonna multiply them, and we're gonna multiply them, we're gonna multiply them, like that. This is the approach that we are doing here. Let's see. This is the definition of the auxiliary polynomial for the product check. So this is it means it's a multilinear polynomial. So v tilde of 0, x1 to the x1 will evaluate to a same value to the f tilde steps. And the value at v tilde of 1, x1 to the xn will return the same value, v tilde of a x1 to the xn, 0, and x1 to the xn, 1. Okay. And actually, the reason we are doing the product check is that for the permutation check, so we're gonna define the f tilde just like this, f of x over g of x. So it's just interpolating the same result of f of x over g of x for the given Boolean hypercube. We should be able to interpolate a unique multilinear polynomial. So the grand product of f tilde equals to 1, then we can do the permutation. We might be able to do the permutation checks between f and g. This is actually what we want to do. Okay, let's move to the next part. Okay. And then for actually for the first round, we're gonna define a R1 head of x, and the value will be look like that: v tilde 1 comma x minus v tilde x comma 0 times x comma 1. Because we define the v polynomial in to satisfy
fx plus 0 basically.
like this, to satisfy relation like this.
Yep.
So we can expect that this part will become 0 for the Boolean hypercube. So which means that we are doing some zero check actually.
Is it just on the hypercube? Because the last slide, the identity, it wasn't specified just on the hypercube.
Specify just on the hypercube.
Even for the v tilde.
V, yeah.
Okay.
Even for the v tilde. Yeah. And then this is the first round, and for the second round, we're gonna define the second auxiliary polynomial R2 hat as v tilde 0 comma x times g of x minus f of x.
Oh, v is a multivariate.
That's f tilde.
Hmm?
V tilde 0x.
Uh-huh.
That's just f tilde, right?
v tilde 0 comma x.
F tilde on the hypercube.
F tilde on the hypercube. Let's check.
Right, that's why it makes sense. That's why it's 0.
Yeah, correct. Yeah. It's correct. Then, let's see. Just move this. Okay. Actually, what we want to do is actually checking the final auxiliary polynomial H hat all over the Boolean hypercube with the n+1 dimensional Boolean hypercube, which means that it will be 0 for every case. Actually, let's try to write down on the whiteboard there.
Join the research club.
Okay. 1 minus x0 times r1 hat x. Actually, will plus x0 times r2 hat x will equal to 0 for all of the Boolean hypercube. Right? And then what does that mean? Okay,
So when x0 is 1, it's just R2.
X0 is 1, it's just R2.
When x0
0 is
0.
0,
it's just R1.
It's just R1.
Yeah. So yeah, we are doing the sum check for the R1, also sum check for the R2. Right?
Yeah.
Doing sum check for the R1 and doing sum check for the R2.
Zero check, right?
Yeah, zero check. Yeah, exactly. The zero check for the R1 and zero check for the R2. Okay.
So we're saying that if we do a product check on H, no, right. If we do a product check on H,
The product check on.
sorry, some check on
We are doing a zero check on H hat.
Okay.
Yeah. Actually, it'll be good to write down with the exact case. Let's say we have a two variables, x1 and x2, and also we have an x0 here. Let's say 0, 0, 0, 1, 1, 0, 1, 1. And the in this case, the v tilde will have a 8 points, 0, 0, 0 to
1, 0, 0, 0, 0, 0, 0.
I'm sorry. 1 0, 0, right?
Yep. 1, 0, 1, 0, 1.
Okay. And by the definition, for this case, actually we're gonna make it exactly same with the f1 to 3, 4, for example. Let's say f0, 0. So f1, f2, f3, f4. Okay. So it will become f1, f2, f3, and this f4. And from v equals 1, it'll become the values when the v tilde 0 and 1 is, which means okay. Let's say this is v1, v2, v3, v4, 5, v6, v7, and v8. And then let's try to draw a line like this. Actually, what we want to do is that v1, v2, v3, v4 is the f value, right? Actually, we want to make we want to make the multiplication of them. So when we think about that, we should be able to multiply them. v1 times v2 is a f1, f2.
Yep.
Let's try to multiply them. And actually, we can also try to multiply them. Finally, it should equal to f1, f2, f3, f4. Actually, what is the v1 and v2 here? 0, 0, 0 and 0, 0, 1. This is actually the v5, right? We are fixing the first two parts and then actually making 0 or n1. So this is actually v5. What should be the v6? We fix the first two coordinates with 0 and 1 and change that with 0 and 1. So actually it becomes the v6. And it becomes a v7.
Okay.
Right? Is that correct? No, no.
I don't. Yeah, not V7. I think.
Yeah. Say V5, V6.
01. Right? V7.
V1, comma 0, 0 is V5, and 1, comma 0, 0 is 0, 0, comma 0 is 1, 0, 0, comma 1 is 1. Actually, the F1 times F2.
Yes.
So F1 times F2 is V5. This is V6. V5 and V6 is, we are actually fixing the first two coordinates using this 0 and 1, 0 and 1. So V3, V5, and V3, V4 multiplied, the result will be V6 here. Okay, we have V5 and V6, and let's try to see what the V7 is. The V7 will be 1, comma 1, 0, 1, 0, comma 0 and 1, V5 and V6. So this should be the V7, right? And what should be the V8? V8 is 1, comma 1, comma 1. So we have only this thing. So V8 equals to V7. No? I'm sorry. 1, comma V7. Okay. This is V7. V8 actually equal to V7 times V8. Nope. V8. 1, comma 1. I think it's correct. Which means that it should equal to, it should actually, it will hold true when only the V7 equals 1. I mean, V8 should equal to V7 times V8. So it will hold true only when the value V7 equals to 1.
So can you explain how you get V6 from V3,
V6.
V4?
V6, okay. V6, the coordinate looks like 1, comma 0, comma 1. And let's see here. 1, comma 0, comma 1 is a multiplication of 0, comma 1 and, I'm sorry, 1, comma 0, comma 1, right? Yeah. 0, comma 1, comma 0, 0, comma 1, comma 1. So 0, comma 1, comma 0, 0, comma 1, comma 1. So this is V3 and V4. So actually V6 is a multiplication of V3 and V4. Yeah, actually it's a little bit difficult to see how the multiplication binary tree works before we actually write down this equation.
That one. So you take one and then you take some value. Let's say in D5, right? D5 is the only polynomial in there that is true, right? So take that as a 1. What happens is you can find what leads to the particular block, which affects actually. So this is so look at the second one. The third. So in this case, n is 8. Yeah. N is 8. N is 7. n plus 1 is 8. N is 7 or 8 for this one. For this one, for this example, is the n 7 or 8?
N7. The N is 7 here.
Yeah.
But actually, by definition, we can compute the V8.
Yeah.
In this case, actually V8 equals to V7 times V8, which means V7 is 1. So the grand product becomes 1.
Okay. So it's the last term, right? Because on the both it says that B is in the field where and all the polynomials are actually x to the x power n plus 1. But when you do that calculations, I'm good n, and then we add one term at the back. Is it? Because we add one term behind for both the B polynomials, 0 and 1, right? So the xn plus 1 is technically, or the 0 and 1 is technically xn plus 1 in here, right?
Yeah. Technically.
So imagine this. So let's say B6, right? Let's say you want to get B6. So let's say B1, so it will be 1, 0, 0, everything on 0. And then 1 will be 6. B6, x of B6 will be 1. And then other thing, so 0, 0, 3, right? So that corresponds to what B6 has here. B6 Yes, but it's not matching you. Yes. So the right hand side, 0 and 1, depends on which one you are at, right? So it's always 0, 1, 0, 1, 0, 1, 0, 1. So it's just what's in front. So what's in front, if you encode it in this, it's 0, 0, 0, 0, 0, 1. And that will result in 1 something. Right, so in this case it's 1, 1, 0, 0. So that, I think that's the ideal. So that you slowly go through it, and then it will become 0, 1, 0, and 0, 1, 1, and then you will go to 1, 0, 1, 0, 1, then you combine them. Yeah.
Okay.
Roughly?
And so every cell is not where you have to match the x1 and x1.
Yeah. And the final one is the same because of the 0 and 1.
x1 on the left and x1 on the right is the same.
Yeah.
You have to match that.
Yeah. So actually, to make this into a polynomial relation, actually in this case we actually had two constraints. The first constraint was that V5, like if we just express it in a bitwise expression, then V5 is a multiplicator of V1 and V2, V6 is a multiplicator of V3 and V4, V7 is a multiplicator of V5 and V6, and V8 will be a multiplicator of V7 and V8, which means that V7 will be 1. So this was the first constraint that we are trying to add here. And the second constraint is that V1 will be equal to F1, V2 will be equal to F2, and V4 will be equal to F4. If we make some polynomial relations that satisfies these two constraints, then it means that grand product of F1, F2, F3, and F4 equals to 1. Okay.
Because the last one equals to 1, it means that everything else is.
Right. I mean, the V8, if the V8 equals to V7 times V8, it means V7 is 1. And then, yeah, actually this is the R1 and the R2 was actually the constraints for each thing. The R1 is the constraints of the multiplication of the binary tree, and the R2 is the expression for the V1, V2, V3, V4 equals to the F. In our case, right here. Actually, F is G over F over G. Actually, if you put here, you put this instead of here, and actually it'll return 0 for every case. Yeah. So the R1 is expressing this binary tree's multiplications, and the root equals to 1. There is an R1 polynomial there, and all the polynomial is expressing that, okay, V1, V2, V3, V4 is equals to the F1, F2, F4. Good. We did the product check using multivariate polynomial, using some check, because it's we can just do a 0 check for R1 and R2.
So, but this is a sum check.
0 check is a sum check.
Yeah. Okay.
But,
But the whole thing is a branch check.
but actually you could, yeah.
So in this case, when we talk about gx and fx, it's the two polynomials that we want to check if it's
Yeah.
equivalent, right?
Right, but actually we're gonna do the permutation check here. So there will be a permutation relation. Actually, if we add some randoms there, and actually the grand product still exists some same value, there will be kind of some permutation. Actually, we need to think about the sigma permutation actually here. This is something pretty similar to what we have seen when I introduced the lookup argument using the sigma function, right? Okay. Yeah, actually we are just doing the product check just by adding the sigma function additionally. Just like we did in the lookup argument check.
But in this case, you are, so to say, permutating
With
the
sigma.
order of sigma, right? Because
Yeah,
sigma
the
maps to
sigma,
another order.
yeah.
Yeah.
Sigma actually will return only 0 or 1.
Yeah.
So actually we can make sure that it's transforming something from a Boolean hypercube from another
Boolean
vertex in the Boolean hypercube.
Ah, okay.
Okay. And in more detail, we are adding some random values there. To make sure that sigma permutation works correctly. This is, you remember the technique that we have used in the permutation check in the univariate polynomial. We actually, there also exists the sigma function actually. And sigma function actually outputs the another root of unity. So because of that, we actually evaluated polynomial and we actually added the x value to the polynomial while add the evaluation of the sigma value to the other polynomial.
So you only use the root of unity on one side and not the other side.
Root of unity on one side. Yeah. Actually, both are the root of unity, but
one uses the same
yeah,
function.
for f actually we are adding x, but for g we are adding
Yeah.
sigma of x.
So
And actually, gonna give you a root of unity. Actually, it'll give you a kind of some transformated some root of unity, like the root of unity
because
like
x
this.
is the original wiring permutation, the sigma x is another permutation. Yeah.
And actually, to make sure that we added some another gamma, and we did some gram product check with each other. In our case, in the multivariate case, the root of unity is actually correspondent to the
Hypercube?
position vector, and the position vector is actually the vertex of on the Boolean hypercube, which means that we can express that in a bit expression. So we can express that in a it means that we are encoding a Boolean hypercube into a some number there.
So in this case, if we are using this, since we are using Boolean hypercube, if we have a lot of wiring, we have a lot of wires, that's a lot of permutation. Does that mean I have to essentially increase the degree of my hypercube?
It doesn't.
It doesn't. It's still the same size?
It's still on the same side. So let's think about only the gamma. F plus gamma and G plus gamma. If the brand product of F plus gamma and G plus gamma are equal to each other, actually it means it's a permutation of each other. But actually we want to add some wiring. So we want to add some index. And actually sigma function actually does that work.
So in
The sigma function is actually transforming the vertex in the Boolean hypercube to another vertex in the Boolean hypercube.
So it's not actually exactly just the vertices of the hypercube. It's the relation between the vertices encoded inside the function.
So actually there might exist some vertex and we are expressing that into a bit operation. So we can express it to another number. And actually it's corresponding, there might exist corresponding vertex. And we are also expressing that to a number. And actually, if it holds true, it's kind of a index permutation. Without this, it's a permutation definitely. But if it's also holds true, even after we add the position information to that, actually it means that it's an index permutation. So we can actually wire the fan in, fan out using that.
So why is the delta mean? Or is it delta? It's like it's multiplied delta.
Delta is a to add the randomness.
Just like normal.
So like why is gamma not enough? I guess.
Why we need delta?
One that to the polynomials, another one adds randomness to the function, the sigma function, or the y. Why is it not
Yeah, I'm like, wow. Yeah.
Actually, yeah.
Because you can't control gamma, then gamma is technically enough, right?
We can control them, but
Yeah.
That's actually my question for the univariate case. I think there's one, the final form of the univariate case also has delta.
Yeah. Actually, I think if we don't use delta, then actually we cannot separate the f and the relation between f and the sigma there. So maybe we might be able to find some sigma or polynomial evaluation value that satisfy the result, why it's actually not a kind of a sigma permutation.
Right, so okay, so without delta, you're just proving f plus s is g plus s, but not
F plus s is g plus
like
s.
as a whole, right? Like without the delta,
Without
then what
delta.
you will be proving is the sum of f and s is
Mhm.
equal to the sum of g and s on those points, but not.
Actually we are checking the grand product here. Yep.
So we need this for hyperplane. So what's the
Yep. We need this for hyperplane.
the multivariate?
Yep.
Okay, so what's the answer again? And what's the reason?
Including delta. Without delta, yeah. I think we can try to make some attack vector there without delta.
It's not necessarily.
Attack vector.
This one, it's not exactly the flex. It's the relationship between the flex. So how we can really like it? No, but it's an index. It's not a flex. Not exactly like because
And that's what I'm saying. I'm saying that
it's
without delta, you're proving
connection
f plus
between
this
indexes.
s function equals to g plus that s function, but not f.
Yes, yes, but
Not,
you
not f is.
you also have, but you need doesn't use the you use the you also have it. It's they use.
Yeah, actually, Kathy, I think we can try to find how to attack that when if we didn't use delta. Yeah, I think I'm pretty sure that we can find the attack scenario without delta. I think. Yeah. Okay.
The thing that is stopping from is sigma. But it's not. So it does the same thing. So this sorry.
Yeah. So we actually have completed all the parts that we wanted to cover during the workshop. So we're gonna have the final breakout session, and then after that we're gonna do the speed run from the day one part one to this multivariate subject.
Okay.
Gotcha.
How long do you want to break
I'm
up?
gonna share the multivariate slide in the Telegram chat. So for the final 40 minutes of a breakout group session, let's try to exactly do this product check and permutation check.
Okay.
And let's try to understand that how we can use this for Plonk.
Okay.
We had L polynomial, R polynomial, and O polynomial. And actually we just wanted to wire the fan in and fan out.
Okay.
Right? This is actually what you want to do. Okay.
So you want to calculate, you want to understand how that works
Yeah.
for hyperplane basically.
Right.
Okay.
You know, we already did the zero check.
Yep.
Yeah. Did we do only the sum check? We
We
did the zero check.
for this.
For for the previous breakout group session.
Zero check. Zero check.
Zero check?
Yeah.
Only some check?
We do some check.
Some check.
We did some check.
We did only some check.
Yeah, some
Okay,
check.
then let's try to do the zero check.
Okay.
And then also the product check, permutation check.
Okay.
Yeah, you can do that.
Okay.
Okay, let's
Hey.
go.
You want to get?
Let's go.
Yeah.
We can do that.
Oh. Time. Yep.
Okay, first, actually, we have visited the abstract algebra on the first day. So, what was a group? Group is just a set, actually, which has a binary operation, which has some properties. So, we are a group, and if what happens if we add me and Wen Kang? If it's a group, like maybe Preston might be the result, right? Basically anyone is. Yeah. So this is just a group, and we have binary operation. And why the result is Preston? Actually, we can't define any kind of binary operation rule there.
Yep.
So we have a numbers, or we can make the group with elliptic curve points and etc. So that was actually the group, right? So because of that, we can also see that Caesar cipher was also a group. The group elements are the alphabets. And what was the result of the binary operation between alphabets? Actually, it's kind of shifting them to another alphabet, right?
Yep.
So we could see that, Caesar cipher is also a group. But there was one problem is that, to use it as an encryption, it's so easy, right? Because of that, how can it make much more difficult?
Make it a multiplicative subgroup.
Yeah, actually we made it as it was an addition group. So we made it as a multiplicative group. We actually chose a generator G, like 19, and we mapped that using 19 to the exponent, the corresponding number of the alphabet, and actually we mapped it. If that actually, it is really difficult to see exactly what the exact number inside of the generator. So this was called the discrete logarithm problem, right? So if we actually have the discrete logarithm problem, it becomes much difficult to see actually what value inside of the exponent of the generator. And then, using this fact, we're gonna we could define another something called a group using elliptic curve points. While we are actually defining the elliptic curve points, we already did a pretty similar thing via the Shamir secret sharing, right? When we started the session, actually we got the QR code with the actually random looking x and y points. We interpolated the polynomial and evaluated that. Actually, ZK evaluated that at 9, and he got drained a kind of 10 cups of coffee. And then, actually, when ZK drained that, ZK needed to compute that, but actually, it was a really big number. So the degree of 6, but the number size was almost 254 bits, which means if you multiply that by 6 times, it's more than 1,000 bits, and the computer cannot compute that. So actually, the method to avoid is actually using the field arithmetization. So when ZK drained that, ZK actually did the field modularizations for every multiplications. So it was the reason why we can compute something in a much more efficient way. So using this fact, we define elliptic curves on a prime field, just like what we did in Shamir secret sharing. And then actually we can compute the the addition, actually we define the addition of points, and then the addition of points is actually defined as the multiplication of x, xp, xq, like yp and yq, etc. And actually we can compute that in the prime field in an efficient way. Okay, so in elliptic curve, we define the basic form of the elliptic curve, which is called the Weierstrass form, which looks like this. And then we define the binary operation between the group elements by a geometrical way. Like, if this is P and if this is Q, we are defining that 3 points are on the same line. So we are defining that P plus Q plus Q plus R equals 0. So we define, okay, P plus Q is minus R. This one. So we find this, actually defining this line, and then find the intersection, and then reverse the y value was the way to compute the group binary operation in elliptic curve. But as we see, actually it includes some edge cases, right? Edge cases like this. Yeah, actually it doesn't have any intersection. So because of it, we need to compute that by some flow control. So it's checking that all the edge cases. So it's not that efficient in when we try to compute the binary operations. Because of that, actually we introduced a much more efficient curve, which is called Edward curves. Edward curves. Actually, Edward curves actually look like that. So it works just like a unit circle. So we can use the Euler equation like this. So gamma is the alpha plus beta, like that. So without any edge cases. So because of that, it's really convenient to compute the result. And also, we have a twisted Edwards curve, and twisted Edwards curves introduced us the pairing functions too there. Using twisted Edwards curve, actually we can define some pairing function. And what is the pairing function? Before we go to pairing, we did the ECDH. Alice, Bob, Carl exist. Alice knows Alice's secret key A, Bob knows Bob's secret B, and Alice share her public key in the form of G to the A, Bob shares his public in the form of G to the B, and they can create a shared key, only Alice and Bob, with G to the AB. And actually I introduced some real example that Carl comes in and accidentally Carl exploited this key, hacked this key, and then Carl wants to check, oh, this is exactly from Alice's public key, Bob's public key, to try to use that. How to check it? We actually introduced the pairing function here, E. Actually will result the same W, like this one. Actually, to be more precisely saying, it's in a group 1, group 2, and the result is group T. Actually, let's just get the intuitive sense. So we are not saying about group 1 and group 2. So if we have two things in elliptic curve points group elements, without knowing its scalar private, we can compare the values. Actually, it is introducing our method in evaluating polynomial in group element form. Yeah. So what was the first case that we have done using the pairings on the first day. The last day, at the end of the day one.
The first thing.
BLS, right?
No, KCG.
Yeah. We did KCG.
KCG.
Oh, KCG.
KCG.
Yeah.
Yeah.
We did KCG.
Yeah,
No?
KCG. Yeah.
Wasn't it?
We were debating about what is in group 1, what is in group 2.
So actually, what was the KCG? KCG was that
Common key.
okay. You have a polynomial, and we don't want to share your polynomial in detail. So we're gonna share your polynomial in a group form. And I'm gonna let Wenkan commit to Wenkan's polynomial. So to let Wenkan commit to the polynomial, I pick some random number R. And Wenkan, would you please evaluate your polynomial at R? And would you please give me that in a group form?
Yep.
So Wenkan give me G to the F of R. It becomes Wenkan's polynomial commitment. And then Wenkan argues that the polynomial evaluates to some value at 9. Actually, this is Wenkan's argument. And then, not to be cheated by Wenkan, actually we are requesting, oh, would you please give me your proof that that is correct? Was actually what we are doing. And to make it, if your polynomial is evaluated at y1 at x1, then let's try to subtract your polynomial to y1. And we're gonna say that this is the first polynomial p1. Right? And then if your polynomial p1 actually is f of x minus y1, the p1 of x1 will evaluate to 0. Right? Because of that, it means you should be able to write that in the form of x minus small x1 times some quotient polynomial. Because it will go to 0 anyway. It means you have a factor that x minus x1. So let's say this is the p2. p1, I think I can compute p1 as a verifier because you already gave me some your commitment here. What I want to do is that, okay, if p1 equals to p2, the evaluation of p1 at a random number r should equal to the evaluation of the random number r of the p2, right? So I can compute the evaluation here in the group 4 because Wenkan gave them to me. How do we compute this one?
GQX is also in group form.
Yeah. So to compute this, Wenkan need to give me the g to the q of r. And actually we are checking that using the pairing. So you take in a group form, we can check the pairing to check it holds true. This was the KGG polynomial commitment scheme in the opening. And when we are doing that, we evaluated those polynomials at a random number. And what is the soundness of this argument here? What is the soundness of this proof?
Not so.
Yeah.
B divided
Right.
the field, the size of the field, something like that.
Right. Because this is a P1, this is P2, and we may have P1, and we are saying that, oh, P1 is actually exactly same to P2. But if actually Wenkan cheated on us, maybe P2 will look like this, and there might exist some maximum D plus 1, D plus 1, right? D plus 1 intersections, and actually it will be kind of some false cases that are examined actually saying true, even it's not true. It was the soundness, it was the Subaru-Zippo lemma, right? And actually, rather than making it in a interactive form, actually we can try to create this in a non-interactive form. So transforming interactive pairing to a non-interactive pairing is actually called the Fiat-Shamir transformation. And how did we do that? In KG3? Yeah, we made tau. We made a tau which might be Alice, Bob, Paul, Davis, some randoms, and then actually we could create the powers of tau through the multi-party computations, right? And then if we have that tau, actually we can still evaluate some polynomial in the group by doing group operations using powers of tau instead of knowing the exact value of the mysterious tau. Then it will actually successfully transform our protocol from interactive setup to a non-interactive setup. This was the Fiat-Shamir transformation using the trusted setup and multi-party computation. Thank you so much. Okay. And so basically what we have done is a checking pairing.
It's what? It's new?
I mean, we actually using pairings, we have checked the multiplication of a polynomial because we have done the f of x minus something. Y1 is a g of x and q of x and something. So it's a multiplication of a polynomials, and we are letting you share g and q in the form of a group element, and then actually we are checking the, let's say g to the small g, g to the small q, and we are checking the pairing like, oh, it should like this. So while we are having only this thing, we can try actually this equation holds true on the group with the group elements using pairing. So we could do some multiplication of polynomials there, which means that we can design to check the relations between polynomials, many things. And the first thing that we have done was the batch opening of KGG polynomial. So rather than open only one value, actually we can let Wanseob open 3 values at once. So Wanseob, would you give me your 3 numbers and would you interpolate them in a new polynomial? So Wanseob actually gave me a new polynomial like this. It will interpolate like 3, 4, 5, interpolate some values, so we are sharing R of x. And then we can also check that, oh, this Wanseob's sharing 0, 3, 1, 4, 2, 5 is actually on the polynomial f. We can check it like, okay, Wanseob, I'm gonna subtract your polynomial with the remainder polynomial, and it should be able to be divided by a 0 polynomial, which is actually vanishes on those values, and you should be able to give me your quotient polynomial. So we designed a new polynomial relation between these 4 polynomials. Before that we had some relation between 3 polynomials, and we now have added one more polynomial. So this thing is how to design polynomial IOPs. So it was kind of our second polynomial IOP that we have designed. It was a batch opening. And actually, Wanseob already shared another thing, that f of x minus y1 actually f of x is evaluated to y1 at x1. And this is the second information Wanseob shared with us. So rather than checking that twice, we can check it at once by doing a random linear combination, it introduces the batch evaluation of a multiple polynomial relations. Okay. So now we know how to design the polynomial IOPs. Using this fact, we're gonna try to design a polynomial IOP to prove the result of a computation. So in computation, what do we have? XOR, or AND, etc. And then we can say that, okay, let's try to prove some binary operations, and let's only try to focus on the multiplication at first. So we're gonna have a left input, left fan-in, right fan-in, and its multiplication will equal to fan out. And actually, if it holds true, we should be able to make it like this. And then, okay, how can we check this equation in an efficient way? We need to make some range to check this equation. So, okay, let's make L interpolate to a given values 3, 4, 5 at which values? At which values? Huh? Less than? No. I mean, we're gonna let L interpolate 3, 4, 5 at some x values. Yeah. So L of omega 0 will evaluate to 3, 4, 5, like that. And also for the right fan-in polynomial, 4, 4, 4. And the output will be like 12, 16, 20. So we have a L of x now, which has degree 2, and R of x, which has degree 2, O of x, which has degree 2. And then if we multiply L of x and R of x, and then subtract this with O of x, actually it will evaluate to 0 for the given range, the z of x, where z vanishes to 0 on the root of unities, times q of x, some quotient polynomial. And if we use the root of unity, the 0 polynomial is pretty easily computed. What is it? x to the 3 minus 1. Right? It's 3 minus 1. Is that correct? Okay. And q of x. Yeah. So this is the QAP. We designed the quadratic arithmetic program. But so because of that, if we actually prove that, oh, Wanseob shared left polynomial, right polynomial, and output polynomial, and I asked Wanseob that, oh, please give me your quotient polynomial, and then let me prove that using pairing. It means, oh, your left and right polynomial is exactly a multiplication relation between your outputs. So we prove the quadratic arithmetic program. But it's not enough to express all kind of programs because we missed addition. So we invented some way to put something into this left polynomial and right polynomial in a way using selector it's the next thing. Using alpha meta? No. Yeah, using linear combination because we are actually constraining that with rank 1. So using the random constraint system, we are actually okay. Let's say you have a bunch of indices. You have a Wanseob has a bunch of indices like that, and then you can put your witness using a linear combination to this left input or to the right input. That was a R1CS actually what we have done. So R1CS actually has some design rules like we have a multiplication gate, it always outputs witness, and actually multiplication gates actually can accept 2 inputs to fan in, and each fan in is actually a linear combination. And this is actually what we have done using R1CS. So using R1CS, we can express some program to a QAP. But it's still not enough. Actually, what's the next step? Hiding. Actually, it doesn't hide value exactly. It's hiding value a little bit in a group form, but actually we can brute force attack or we can get some hint from there. So to completely hide the value, the basic approach that we are doing is adding salt, just like Peterson commitment, and actually what we have done in the Schnorr signature on the first day. So using that, okay, we're gonna add some random thing, and let's use that in the growth 16 protocol. What's the growth 16? So growth 16 is just kind of a very simple thing. We are just doing QAP, but it's not hiding information completely, so we are adding some salt. That's growth 16. And after that, recently, some people like Ariel, actually they invented a new protocol. I mean, how to define the arithmetizations, how to define the circuits. Okay, so rather than just stopped by the QAP and R1CS, we know how to design this relation between polynomials. So, okay, what about if we design the operation gate in a much more some creative way? That was the problem. So how can we do that? For example, let's say, okay, we have some value, 3 and 5, and actually this is the gate is multiplication. And in this case, we have a 2 and 4, the gate's actually plus. Let's use a multiplication and addition on paper right now. And 4 times 4 is actually a 15, 6, and 16. Okay, then how can we interpret this into a polynomial relations? Okay. So we're gonna have a we're gonna interpolate this anyway into L polynomial. We're gonna interpolate this anyway to the L polynomial and O polynomial. And then L times R minus O only for these selectors. So we're gonna have another selector polynomial and selector. This selector will actually returns 1 if the gate is multiplication, and it will return 0 if the gate is addition. So plus L plus R minus O times 1 minus S. It makes sense, right? S will, yeah, this is actually 1, 0, 1. So we can actually define a new polynomial relation. But actually, sometimes, not sometimes, we would love to actually use this value to here. because we need to able to actually use some values as a fan in from some fan out. To connect those values, we need wiring. We need some wiring like this. So in this case, it should be like 3 times 5, 15 goes here, and it will be like 60. And we're gonna use the 2 plus 3 becomes 5, and this as a fan-in for the first gate, and etc. Let's try to label them: W1, W2, W3, W4, W5, W6, W7, W8, and W9. In this case, we can see that W2 should equal to W6, and W3 should equal to W7. How to make sure? What? Yeah, we need to define another polynomial that makes sure that a vector of W1 to the W9 and W1 and W2, 6, W3, not W3, W7, W7, W4, W5, W2, W3, W8, W9. Actually, these two polynomial, two vectors are equal to each other, which means that they are permutation of each other. To make sure that, we need to know which index to switch to each other. Okay. To do that, we did the permutation check. And to do that, we needed to do the product check. But product check doesn't make sure us that it's exactly the permutation. For example, when we do the product check, three, 4, 6. Actually, the grand product of these 3 values will give us like 48, no, 72, 72. And its permutation definitely will give us the same value, definitely. But actually, we can make the same value with different numbers, like 3, 8, 3 will give us the same value, 72. So to prevent this, actually, doing a product check is not enough for permutation check. Rather than that, we're gonna add plus 1, plus 2, plus 3, plus 1. No, not like this. Plus random plus R, right? I'm sorry, random R. For example, let's say we are adding a random. Let's pick a random number here. What about 4? 4, 2. Thank you so much. Okay, then we're gonna have 5, 6, 8, and the value becomes 30 times 240. Right? Yeah. That's 8, 6, 5 definitely will become 240. In this case, 4, 5, 10, 5.
Yes.
It's 250.
Yes.
Oh, different. Oh, they are not permutation of each other. Okay. To do that, okay, if f of x, the evaluation of this polynomial over the multiplicative subgroup, which means the root of unities, is a permutation of g of x, then the grand product over the multiplicative subgroup of f of x plus some random number should equal to grand product of g of x plus some random number. That's the permutation check that we're gonna do. So we're gonna say this is f prime. We're gonna say this is a g prime, which means that f prime over g prime, the grand product of f prime over g prime will equal to 1. So we know how to do that. For univariate polynomial, how to do that? Yeah, let's see how to do that. For univariate polynomial first, for the univariate polynomial, we define a new auxiliary polynomial t.
T, yes.
And make it actually have some values, just like t of omega x, it actually equals to t of x times f of wx? No. Am I wrong?
I think you're right. Let me check.
I think it's correct.
Yeah.
Yeah. Then if you make like this, then it should look like 1. And actually, right, and we make t of 1 to equals to 1, right? Like this. And then at the end, the t of omega to the n actually equals to t of 1, f1, f omega n minus 1, which means actually this is t1. So it means f of 1 times dot 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 f of omega to the n minus 1 actually equals to 1. So we are just examining this relation by checking the pairing. Renkan, would you please try to compute your t polynomial? And please give me your commitment to the t, g to the t of y. And then I would love to evaluate that on actually, yeah, I would love to evaluate that t of omega r equals to t of r times f of r there. So, yeah. This is actually what we are doing for product check. And then we can do the permutation check. Then actually we can do the Plonk protocol. There was a univariate Plonk, but it also has some limitation that interpolating a very big data to a polynomial costs a O of n log n cost. So if we discovered another approach that using a multilinear polynomials instead of interpolating those things on a univariate polynomial. Okay, and yeah, we are almost getting done. So for the univariate polynomial, for the multivariate polynomial, we defined some hypercube using a Boolean values.
Yes.
And it means like we're gonna have some vertices on some space, hyperspace, and we should be able to assign some values into them. This is actually how the multivariate polynomial looks like: x1, x2, and x3. Then we should be able to assign some values over there: 3, 4, 4, 4, 4, 3, like this. Okay. So we can encode some data, some vector into univariate polynomial, or in this, like this, into a multivariate polynomial. And if we interpolate this to the multivariate polynomial, then how we can check the L times R minus O holds true equals to 0 holds true for a given range. How to do that? In the univariate polynomial, actually we use the range using a multiplicative subgroup, and we use the quotient polynomial there. And in multivariate setup, actually we are using hypercube instead of this multiplicative subgroup, and we are checking that if this holds true, if we multiply some which polynomial?
EQ polynomial.
EQ polynomial.
Yeah.
Then actually
On X and some random vector.
yeah, with the X and some random vector, actually
Equals to
yeah,
yes.
it will give us the same value if we think about it's a polynomial regarding to y. Then actually it becomes a multilinear polynomial to us. But actually, if we just put the random r here, it's putting actually multiplied by some random evaluations by the equal polynomials. So it means that L times r minus O is always 0 for over the Boolean hypercube. That was a zero check that we were doing. And then, okay, we know now how to do the zero check. And this is the actually product check in the univariate polynomial is also actually doing the zero check at the end. The zero check is the final step, checking the polynomial identities. And then in multivariate setup, product check. Okay. Okay. Yeah. We have a just like we defined t in the univariate polynomial. Now we define a multilinear polynomial v tilde v, and actually v tilde will actually satisfy a condition, and I'm gonna assign some values. Let's say we are defining that in a two-dimensional Boolean hypercube, and the v is actually 2 plus 1 dimensional hypercube in this case. So I want to assign value in this binary tree first. So this is v1, v2, v3, v4, v5, v6, and this is v7. And I'm gonna label that with the position vector 2. Starts from 0, 0, 0, and 0, 0, 1, 0, 1, 0, 0, 1, 1, and now it starts from 1, 1, 0, 0, 1, 0, 1, now it becomes 1, 1, 0, then v8 will be 1, 1, 1. It's not here. Now let's try to define that. I hope v5 equals to v1 times v2. I hope v6 equals to v3 times v4. And I hope v7 equals to v5 times v6. This is what I hope. And I hope v8 equals to v7 times v8. So therefore, actually v7 equal to 1, and which means that v1 times v2 times v3 times v4 equals to 1. So if I could define a polynomial v to satisfy this equation, and plus, what if the V1 equals to F1, V2 equals to F2, V3 equals to F3, and V4 equals to F4. If I make some two relation for this one and for this one, then actually I can make sure that the evaluation of F and the grand product of all the evaluation of F will equal to 1. Yeah? And, okay, let's try to write down like this. V1 is a, V1, V000 times 001, actually is actually V5 is V100, and 3, 0, 1, 0, 0, 1, 1, 3, 6, 1, 0, 1, 3, 1, 0, 0, 3, 1, 0, 1 equals 3, 1, 1, 0. Okay. So let's not find anything to 3, 7, 1, 1, 0, 1, 1 equals 3, 1, 1, 1. Okay, now we have some pattern. Which pattern? We have a 1 here. Okay.
You have 0, 1, 0, 1, 0, 1.
Yeah. Actually, it looks like, oh, there's some pattern. This one is actually this one, and 0 and 1. This one is actually this one, and 0 and 1. This one is actually this one, and 0 and 1, and 0 and 1. So using these, okay, great. So we can say that first, how to make this relation. It starts from 0. X1 is 0. So V 0, comma, X equals to, this is the first relation. The second relation, V, let's say this is an X. X, comma 0 times V, X, comma 1 equals to V, 1, comma X. So we define two relations. And we're gonna check these holds true all over the Boolean hypercube, doing a batch evaluation. Then we can make sure that, oh, V F1 times F2 times F3 times F4 equals to 1. So we know how to do the product check on the multivariate polynomial 2.